of solutions, and I think we just had a few more slides here. So some properties of solutions. Sometimes we talk about a semi-pyramidal membrane, and it's basically a membrane. Cells can act like membranes. You can actually have like an actual membrane, but basically it allows certain size particles and molecules basically to pass through, and other ones are not able to pass through because basically of their size. So although a lot of times if you were looking at something that can be used as sort of a membrane, you wouldn't be able to necessarily see it, but there is sort of like a hole, if you will, in between. And that hole would allow certain size molecules and particles basically to pass through. And obviously, if you had sort of a larger particle, it's going to get kind of stuck as it tries to pass through. So again, certain cell membranes sort of work like that. They kind of work as sort of like a membrane and a filter to let certain things pass in and certain things pass out of the cell. Colloids are much larger than solute particles in solution. Remember that a solution is made up of a solute, which is the smaller part of the solution, and the solvent, which is the larger part of the solution. And things that are colloids are much larger than those guys. They are large molecules like groups of proteins, proteins or groups of molecules or ions together. They are homogeneous mixtures, which means they look the same throughout. They don't separate or settle out. They're small enough to pass through filters like filter paper. If you had like a funnel, filter paper action going on there. They're small enough to pass through there, but they're really too large to kind of get through the hole here in a membrane. And that's different than a suspension. A suspension is a heterogeneous type of mixture. It means it's non-uniform, and very different than solution or colloids. These things could also be usually seen sort of with your naked eye. They are trapped by filters and semi-pyramidal membranes. They really don't sort of pass through either of these things. So here's sort of a picture of that. Our suspensions, which is our little red squares there, will settle out, where our colloids and solutions will still kind of float around in the solution. If we were to filter it through a piece of filter paper, we would see both. Again, the solution, the colloids are small enough to go through the filter paper, but it will catch basically our suspension. I want to say used to do experiment where you added sand or you added charcoal or something like that at the end, and with a dialysis bag, and that was sort of your suspension. As you put that through a filter paper, for example, with sand, it obviously wouldn't go through, and that would be your suspension. Here's a membrane, and again, it's going to allow those kind of smaller size solution particles basically to float in and out of the membrane, again, going to kind of trap the larger guys within there. That brings us to osmosis and dialysis. And osmosis is sort of the natural process by which solvent molecules will kind of pass through a membrane, and in an effort really to dilute a higher concentration. So typically speaking, we will see, the solvent molecules move from a lower concentration to a higher concentration, again, in sort of an effort to dilute down the higher concentration. So, if we had, again, sort of a tube that was separated by a membrane here, and again, basically on one side, maybe you had some salt water, and obviously you had regular pure water on the other side. Pure water has really no osmotic pressure. There's nothing dissolved in it. It's basically lower concentration than salt water. Salt dissolved in it gives it a higher concentration. So by the process of osmosis, what we would see is the water on the left-hand side would decide, well, I want to come and cross the membrane and start to dilute down the salt water. And it will really continue that process until it hits really something what is just referred to as the osmotic pressure. And basically the osmotic pressure is atmospheric pressure kind of pushing down back on those water molecules as they are coming across, and it stops really the flow of additional water molecules to that side. The osmotic pressure does depend on sort of how many particles are dissolved in a solution. The greater the number of particles kind of dissolved, the higher the osmotic pressure that's involved. Pure water has no osmotic pressure. So for example, we could calculate or look at what is sometimes referred to as a way of measuring osmotic pressure is through something that is referred to as osmolarity. And it really is basically sort of referred to as osmolarity. There is I times the molarity. Molarity, again, remember, is moles per liter. And I is basically the number of particles there are in the solution. And if you had, say, a potassium chloride solution, in solution that would break apart into a potassium ion and a chloride ion, which is basically one ion, two ions total. And that would be different than if we had something like a magnesium bromide solution. When it's in solution, it would break apart into a magnesium ion and two bromide ions, which means a grand total of 3 particles per each of those. So if we were to basically calculate the osmolarity, let's just say we had the exact same concentration of each of these solutions. Let's just say we had if I could find my pen, where that thing there, there's. If we had a 4 molar solution of potassium chloride versus a 4 molar solution of magnesium bromide, we could calculate the osmolarity of each of these. So the osmolarity of this guy, again, I would be 2 because there's 2 particles. So it would be 2 times the molarity, which would give us 8 molar or 8 osmolarity. If we look at magnesium bromide, which has the exact same concentration, but it breaks apart actually into 3 ions, which means I would be 3 in this formula here. We would take the osmolarity would be 3 times our 4 molar, and we would end up with 12 osmolarity. Bigger number here, greater osmotic pressure in this solution, because there's a lot more molecules that are basically dissolved in there and floating around versus the osmotic pressure here. Water, again, has no osmotic pressure because it's a pure substance. There's nothing dissolved in it. There's no particles floating around. So water actually has no osmotic pressure in that case. Any questions on that there? So you could obviously have 2 solutions that have the same molarity, but because it's an ionic solution, if they happen to break apart into more ions in one versus the other, that would translate to probably a greater osmotic pressure, because again, more particles, more pressure basically happening. When we talk about osmosis and it flowing, that's the idea of, we could kind of reverse this process, which is sort of the idea of reverse osmosis. Reverse osmosis, we basically apply a pressure greater than the atmospheric pressure back down on this. And basically what that does is it kind of pushes everything back the other way. So push everything back the other way. And if you have a really good filter here, you could catch all the sort of particles and stuff like that. And what you'll end up getting on the other side would be some pure water coming back through this way. And again, with a really good filter kind of in the middle there, you catch all the sort of impurities in there, and end up with pretty pure water by sort of applying that reverse osmosis there. Any questions on that there? Here's a prettier picture, I guess, than what I drew. But again, osmotic pressure pushing back down, going to stop the flow of solvent molecules into here through this sort of membrane. Now, there's a couple of different ways that we can describe, a solution, and that is as being isotonic, hypertonic, or hypertonic. So let's start with isotonic solutions. Isotonic solutions basically exert the same osmotic pressure as body fluids. Most IV fluids are isotonic. And basically what that means is, we'll use our common example in these type of situations is, if we put something like a red blood cell into an isotonic solution, basically what will happen is the osmotic pressure on the outside and inside the cell are basically the same. And that means what we would typically get is a nice flow of sort of water in and out of the cell really acting as obviously a membrane to allow things to flow in and flow out. And the red blood cell will be very happy. Nothing bad will happen, which again is why obviously our IV fluids are isotonic solutions. Obviously, if you're getting an IV, you might be in some trouble. So you don't obviously want to give somebody something that's going to kind of mess up their cells. So you want to make sure it's not going to cause a difference in pressure within their cells in their body, and obviously what you're sort of giving. Now, what is sort of considered an isotonic solution? Isotonic solutions are a couple we sort of think about, and it's 0.9%, say sodium chloride mass the volume. And that is also sometimes referred to as a saline solution. It doesn't necessarily always have to be sodium chloride. It could be something like potassium chloride or something like that, or just a saline solution. But 0.9% is considered sort of isotonic, and also 5% glucose is also considered a isotonic sort of solution as well. So these two numbers are important when you're dealing with isotonic, hypertonic, and hypertonic to help you make the distinction as to whether or not that solution is isotonic, hyper, or hypertonic. So let's talk about the other ones here. Hypotonic. Hypo means less than, which means that the solution outside of the cell, for example, is less concentrated than the actual cell itself. So if we take our same sort of situation here and use our red blood cell, and we do put it into a hypotonic solution, what that means is, again, outside of the solution, outside of the cell, less concentrated than inside the cell. So what's going to happen in this particular case is basically the solution outside is going to sort of decide, well, I want to go and dilute the red blood cell. It's more concentrated inside the cell. So we're going to get this sort of rush of solution into the red blood cell. And in this particular case, that's going to cause the cell here to swell and probably burst at some point. And that is what is known as hemolysis. So we'll get this swelling that will occur as the process of osmosis begins, and we'll get hemolysis basically occurring. Now, hypertonic, hyper means more than or greater than. And basically what that means is the solution, for example, outside of, say, a red blood cell, is actually more concentrated than inside the red blood cell. So if we take our red blood cell here and we put it into a hypertonic solution, now because outside of the cell is actually more concentrated than inside the cell, osmosis is going to happen again. The difference, though, is the cell is going to decide, I want to try to dilute down what's on the outside of me. And basically what we're going to get is all of this sort of liquid, if you will, or solution in the cell is going to escape the cell in an effort to sort of dilute the solution down outside. The resulting of that is the cell will start to shrink and go through what is known as crenation, and we'll get this red blood cell that starts to shrink up and shrivel as it lost basically all of its sort of water. Any questions on that there? So let's take a look at maybe some examples here. This here. Let's say we take our red blood cell and we put it in the following solutions. Let's say we put it in, we'll go with 0.3% sodium chloride solution. Let's say we put it into a 5% glucose solution. Let's say we put it into a 12% glucose solution. And let's say we put it into, say, pure water. So take a second and decide in each of these cases, will the cell be okay? Will it shrink? Will it burst or swell? We'll go through crenation, which means shrinking. Or will it swell and burst, which means hemolysis. So take a couple of minutes here and decide what's going to happen to our red blood cell if we put it in these solutions. Let's take a look here. So again, obviously, to help you make these decisions, sort of remembering what we just talked about, which is what are basically isotonic solutions, and that's 0.9% basically sodium chloride and 5% glucose. So when we look at, say, the first one here, which is 0.3% sodium chloride, it is as simple as 0.3 is less than 0.9. So that means that that is less than. Less than means that it's going to actually be a hypotonic solution because it's less than our isotonic solution. That means that basically outside of the cell is less concentrated than inside the cell. And that is going to cause all of the water to run into the cell. And that's going to cause it to swell and obviously burst and go through hemolysis here. Any questions on that particular one? If we look at 5% glucose, 5% glucose is an isotonic solution. So 5% glucose is isotonic, which means that this solution is going to be okay. Our red blood cell, pretty much nothing bad's going to happen to it. Again, it's sitting in a solution that has basically the same osmotic pressure, which means fluid can flow pretty equally sort of in and out of the cell, and nothing really bad's going to happen in that particular case. Any questions on that one there? Looking at 12% glucose, obviously if 5% is isotonic, then definitely 12% is not isotonic. So 12% is obviously higher than or greater than 5%, which means this would be a hypertonic solution, greater than. And because it's hypertonic solution, what's going to happen in this case is outside of the cell is more concentrated than inside the cell. So again, the cell is going to decide to try to dilute the outside of this solution. That's going to cause the cell to start to shrink and go through what is known as crenation. And again, not a good situation that's going to happen in that particular case. Any questions on those three there? It then leaves us pure water here. So pure water, and again, sometimes people see water and think, well, it's water, so probably okay. But as we just talked about a second ago, pure water has no osmotic pressure, which means it's technically a hypotonic solution, which means it's less than the red blood cells. So again, in this case, what's going to happen is outside the cell is less than inside. We're going to get that flow of water into the cell, obviously causing it to swell and burst, which again is our osmosis. Any questions on how to identify isotonic, hypertonic, hypotonic type solutions and what's going to happen? Okay. And obviously this table sort of describes what we've been talking about in terms of the flow in and out of the cell and the different types of solutions. Here's sort of graphical representation of what we've kind of been talking about. And the first one here, again, is this isotonic. So we got nice even flow in and outside of the cell. Nice donut, if you will. Our hypotonic, which is less than, again, outside of the cell, is less concentrated than inside. So everybody on the outside is going to rush into the cell. Again, as you can see here, causing it to swell and burst. Jelly donuts. Hypertonic solution means outside of the cell is more concentrated than inside the cell. And again, that means everybody from the cell in terms of water and stuff is going to run out of the cell, going to start to shrink and obviously go through crenation there, which is not the best situation. This table here is talk about some of the stuff that we did talk about and some stuff we didn't talk about. So we didn't really talk about those guys. But we did talk a little bit, obviously, about osmotic pressure, osmolarity, and obviously these solutions here. One last thing in terms of this chapter here is about dialysis. Dialysis is a process sort of similar to osmosis. It allows small solute molecules and ions to basically pass through, but retains, again, sort of those larger ones. Kind of the same ideas we were talking about earlier with the semi-permeable membrane, and kind of like the experiment I think was a couple of weeks ago. You get this dialysis bag, although when you look at the dialysis bag, if you looked at it sort of in person or use it in person, when you would look at it, you can't really see that there's holes, but there basically are holes in it, if you will. And again, these holes are obviously size limiting. And as certain size guys try to get through, as we talked about before, still not going to be able to do that. Other size molecules can pass through with really no problem. For example, our body, again, does sort of filter out certain things, waste products and stuff like that. So we don't sort of absorb those things and let other things sort of pass through that we do need. In sort of a laboratory situation, sometimes you may maybe you're working on a protein or something like that, maybe put your protein in a dialysis bag, maybe put it into a solution where maybe, it has the same pH as, say, the body or something like that. You could kind of equilibrate the protein to the same sort of environment, for example, that you would find in the body. And obviously you could run your experiment sort of in a similar fashion to how it would be sort of in nature and naturally occur in that environment to sort of see it. So sometimes in, research, people will do sort of use things like dialysis bags to sort of try to create an environment that's similar to whatever they're studying. Again, like, for example, if you're studying something that's maybe in your stomach, that's more of an acidic environment. So you may take a protein and sort of let it sit in an acidic solution and, kind of put it in like a dialysis bag where the protein really can't escape, but it will allow, the more acidic solution to kind of flow in and out of the bag and sort of equilibrate the protein to that environment. And again, that's sometimes helpful, if you're trying to sort of simulate something in the laboratory that maybe occurs sort of in nature. And this is kind of similar to the experiment a couple of weeks ago as well. Again, you had a dialysis bag, I think, allowing certain size particles to pass through. And, if I remember in that experiment, every so often you would take the water on the outside and test it and see what was able to pass through the bag. Um, and, you waited maybe another 20 minutes and took another sampling of the water and kind of see what was out there. And I think at the end, you popped the bag open and saw what was left inside. Clearly, as you can see here, these sort of larger molecules are not going to be able to really be able to pass through. And again, they would be trapped in this sort of situation. Any questions on these last few slides here from solutions? I just want to make sure I went over it with you guys as well. But, while you're maybe thinking of some, I did touch upon it today during lecture, but I do maybe we'll take a couple minutes here if there is sort of no questions to ask. Again, really more the calculator aspect of sort of punching these things in. And again, that's usually in my experience where a lot of people sort of struggle in terms of, two things really, like, and I think there was kind of a question earlier today about it as well, which equation should I use? And, how should I punch it into my calculator? So why don't we talk a little bit about that, just a little bit more, that hopefully maybe will help clarify some things. So we have a number of equations or formulas that we saw in this chapter. Obviously, we had our KW equation, which is our H plus, and our OH minus, which is our 1 times 10 to the minus 14. We had kind of our grouping of pH, which is minus the log of the H plus. We also had our POH, which is minus the log of the OH minus. Then we also had another grouping of, if you're given the pH, you could get the H plus concentration from that by taking the inverse log of the minus pH. And if you have the POH, again, you could get the OH minus concentration by taking the inverse log of the minus POH. So these are sort of our grouping of formulas here that we had in the acid-base chapter. And obviously, as we talked about a little bit today during lecture as well, it's important to make sure you understand sort of how to properly punch these guys into our calculators. So when we first off are looking to solve for any type of concentration, we do have really two options, and concentration is typically molarity, which is moles per liter. And that again is usually in acid-base chemistry represented by either trying to solve for H plus or OH minus is what we're trying to solve for. So this is usually how it looks, if we're trying to solve for either one of those things. And that really is the concentration. And really at this point, based after today's lecture, we actually have two options to do that. You would either use KW, or you could use either of these sort of grouping of equations. Now, most of the time you would choose KW, perhaps, if you had the H plus or OH minus concentration, this would be a pretty good one here to choose. If you happen to have the pH or POH, you might want to go with one of these two as a way to get to the H plus or OH minus concentration. Again, if we're using KW, as we've talked about, if we were doing the H plus is equal to 1 times 10 to the minus 14 divided by, just to say the concentration of the OH minus was 3.2 times 10 to the minus 8. Again, in terms of calculator and putting those in, we would do it like we've been talking about: 1 exponent button, negative button, and 14. That basically takes care of this guy. We then would divide it by 3.2 exponent button, negative button, and 8, which takes care of the bottom guy, and then obviously hit equals. And again, in this case, if you did that, in case you're playing at home here to see if you're getting the same thing, we got 1 times 10 to the minus 14 divided by 3.2 to the minus 8. And on my calculator, again, it doesn't necessarily give it in scientific notation, but if you sort of put it into scientific notation, you end up with, I believe, 3.1 times 10 to the minus 7 molar. And again, on my calculator, I had 0.00000031. And that would be the proper way to make sure that you punch those in. Again, if you happen to have been given the pH value, let's just say the pH was, 8.54. Again, just making up that number. We could use one of these guys, which again is the inverse log. So as I've said earlier today, on most people's calculators, upper left corner, there's usually a second button, a shift button, something like that. And then typically you would hit the log button. And again, you want to make sure that you do make it negative. And by the way, again, when you do this, that typically would pop up a 10 and a caret on most people's calculators. And obviously you hit the negative and 8.54, and then the equals. And if you did it that way, you would end up with, looks like something like 2.9 times 10 to the minus 9. And again, this would be molar here. So again, what I just typed up here is if you did have a display calculator, and if you did not have a display calculator, as I mentioned earlier, you basically kind of has to do these guys sort of backwards. Usually has to start with the numbers. So again, if your calculator is a non-display calculator, and if you're not sure if it is or not, you could hit log, and if it says error, that is a non-display calculator. If you hit log and it says log, it's a display calculator. But if we were going to do this guy with a non-display calculator, again, we would actually, this particular one would work the same. We would actually do this one the same for this calculation. But if we had a non-display calculator for this guy, we would actually start with the number. So you would actually type in 8.54. Then you would need to make it negative on your calculator. And when you do that, again, it will kind of turn this guy into a negative number. And it's at that point you would then hit your shift or second button and your log button. And usually that would then just give you the answer at that point. You don't have to hit equals usually. In most cases, again, may not give it to you in scientific notation, but that would give you sort of the right answer. Any questions on how to properly punch those guys in on those two? And again, really, if you're looking for any type of concentration like molarity, what's the hydrogen ion concentration, the hydroxide concentration, the H plus or OH minus concentration. These are your two sort of ways to get it there, either the KW or using the inverse log. So those are really your guys, as a way to calculate the concentration of either of those things, really the acid part or the base part. And again, as we saw in some of the examples today, you could kind of cross over and use them together or separate, kind of depending on the information. As was the earlier question today, when we're talking about H plus concentration or OH minus concentration, that's really telling us, how much of these things are, kind of floating around in the solution, basically. And as I mentioned before, when we get numbers, for example, like this, or a number like this, as for the H plus concentrations, as I said earlier today, you could tell somebody, hey, the H plus concentration is 3.1 times 10 to the minus 7 molar. And that may be, well, that's great. But I was kind of curious, is it acidic, basic, or neutral, the solution? So when we talk about the two sort of formulas in the middle, the pH and the pOH, it's really a way of sort of taking the concentration of your H plus or OH minus, as I was saying earlier, and sort of turning it into, I don't want to say a more useful number, but I guess is a way of saying that, a more useful number, a kind of quicker way of looking at the number where you go, okay, I know that the pH scale runs from 0 to 7 to 14. I know below 7 is acidic. I know above 7 is basic, and I know 7 is neutral. So when somebody says, oh, the pH of the solution is 8.54, that number has a real meaning to me, that, oh, it's 8.54. I know it's above 7, it's basic, rather than, hey, the H plus concentration is 2.9 times 10 to the minus 9. If you were to tell me that, I would then probably have to perhaps go figure out what the OH minus concentration is, kind of comparative values, or even calculate the pH. So the pH, which is really based on the H plus concentration, and is sort of a more simplified version of the number that gives people a really quick understanding of, oh, that solution is basic, or that solution is acidic, or that solution is basically neutral. Same idea here. It's like, all right, I got 3.1 times 10 to the minus 7. Again, not really sure if that's acidic, basic, or neutral. I could calculate the pH, and then that turns that number into a real usable type number, because in my head, I have this pH scale. And now, even though we do and will calculate both of these things, as I mentioned today, it's really important to remember that when you're trying to determine, is it acidic, basic, or neutral, it is always the pH that you should look at. And again, as I said before, it is a very common mistake that people make, that they will give multiple answers to that question of, is it acidic, basic, or neutral? And again, there should really only be one answer. So anytime we kind of want to turn a concentration kind of into a usable number to help us kind of easily figure out, is it acidic, basic, or neutral, we look towards pH or POH to do that. And again, the names really do tell you, what you need when you are using those. If you are using the pH, as I mentioned earlier, pH means you need the H plus concentration. Remember also, again, H plus and H3O plus are the same. So, you need either the H plus, or you need the H3O plus, exactly the same thing. You need one of those two guys, which is basically the same thing, to calculate this. And if you're calculating the POH, again, you need the OH minus concentration here to do that, which is really the basic part. And these two guys are really helpful for each other because of that pH plus the POH is equal to 14 relationship. That really does allow you to, sort of bypass some things along the way here. If you know the pH, you could very quickly get the POH. If you know the POH, you could very quickly get the pH. And that's helpful in a situation if you want the pH, but you're given the OH minus concentration. So you're given the OH minus concentration, you could calculate the POH and then subtract 14 and get yourself to the pH really quickly without even having to actually use the actual pH equation to do so. When we punch these in as well, we want to be careful that we do punch them in correctly. So let's again just say we wanted to know really what this number means. Again, that 3.1 times 10 to the minus 7 molar for our H plus concentration seems like a nice number, but does that mean it's acidic? Does that mean it's neutral? Does that mean it's a basic solution? So because that's the H plus concentration, we could go right into our pH equation, which would be minus the log of 3.1 times 10 to the minus 7. Here again, if you have a display calculator, you should punch this in exactly the way it looks. You should do your negative button. You should then do your log button. You then should do 3.1 exponent button, negative button, and 7, and equals. And if you do that, you end up with here a pH of 6.51. And now this number does really mean something to us. When we see 6.51, we now know, oh, All right, that's less than 7. It's slightly acidic in this case. And again, it's really based off of this number here. This number and this number, they are related to each other. They're basically how we get both of those numbers. But again, having sort of a pH value does give somebody a more sort of, if you will, usable number of what it means in terms of the solution. And obviously we can see here that the solution means that it is acidic in this case. Not a lot, but it's still slightly acidic there. It's less than 7. Again, if you had a non-display calculator, you would be rolling opposite here, which means that you actually would be doing a number first. So you would do the 3.1 exponent button, negative button, and 7. And then you would do your log button. And then you would actually end up with a negative value here. You would actually end up with, at this point, negative 6.51. Then you would hit your negative button, and it will then turn this guy into a positive number, and you would get that. So again, with a non-display calculator, pretty much all the equations to the middle and right here of the screen, you kind of have to work your way backwards, usually starting with a number. And if you have a display calculator, you pretty much roll the equation just like it's written, in your calculator. Any questions on to properly sort of punch these things in? Sometimes half the battle there. Any questions on anything that we've been talking about or anything I can help anybody with?